Welcome back. In this lesson we are going to learn about the predictor-corrector based coupling schemes which can be used in Monte Carlo burnup simulations. Monte Carlo burnup coupling schemes which are based on the predictor-corrector method are basically implemented in all established Monte Carlo burnup codes nowadays. So there are many different variants of these coupling schemes, and I'm going to describe the basic one. It's important to know that all the different variants of this coupling scheme are only conditionally stable, so they suffer from the same stability problem as the explicit Euler method. However, many users of Monte Carlo burnup codes prefer to use the predictor-corrector based coupling scheme, which is sometimes very hard to justify, as you will see later. So let's start with the description. So I'm going to describe the scheme on two time steps. So I will have time t0, t1 and t2. So at time t0 the system is described by the initial nuclide field vector n0. So this is given by the input file. So at first the Monte Carlo solver is called in order to calculate the neutron flux in this system. So the solver will return the flux phi 0, the flux in the system at the time t0. The predictor-corrector scheme at first doesn't differ from the explicit Euler, so it's using the initial nuclide field vector and the initial flux phi 0 to calculate the nuclide field vector at time t1. However, this nuclide field is marked as the predictor nuclide field. This nuclide field is then used in a new Monte Carlo simulation, so the Monte Carlo solver is called again and it will return the new flux, which is called the predictor flux at time t1. So far this looks like the explicit Euler base coupling scheme. However, here comes the difference. The predictor-corrector scheme combines these two fluxes together. It calculates the average value of the flux phi 0 and the predictor flux. So it calculates the average value. So I'm going to call it the corrector flux phi c0. So the idea behind this scheme is that the corrector flux is a better representation of the neutron flux over the time step than the initial flux phi 0, because it combines the initial flux with the flux which is predicted at the end of the time step. So if by chance the time step was very long, the neutron flux would be changing a lot, so the beginning of the time step flux would not be a good approximation for the flux over the whole time step. So then it is believed that the corrector flux would be a more suitable representation of the neutron flux for the burnup simulation, for the final burnup simulation over the time step. So the last step here is to use the corrector flux and redeplete the fuel with this corrector flux. So there is a new burnup calculation now. The burnup solver is called again, and it is using the corrector flux and the initial nuclide field N0. And we will obtain the final nuclide field for the end of the first time step. And the whole procedure now repeats for the second time step. So the Monte Carlo solver is called in order to calculate the neutron flux in the system in which the nuclide field N1 is introduced. So well, I don't have much space here, so I will call the solver and I will obtain flux phi 1. So this flux may differ to this predictor flux or this corrector flux, because it is based on the criticality calculation in which the system is described by this new vector N1. Alright, so now we have the flux phi 1 and the nuclide field vector N1. So again we are going to run a depletion simulation and we will obtain a new nuclide field vector N2 predictor nuclide field. And again we are going to run a Monte Carlo solver to obtain the predictor flux N2. Now we will combine the flux from the beginning and the end of the second time step into the corrector flux, and we are going to use the corrector flux to obtain the final nuclide field N2, and we are going to use the N1 nuclide field vector as the initial state. And the whole procedure will then repeat for the third time step, and so on. And here we have the description of the basic variant of the predictor-corrector coupling scheme. So we start with the system given by the initial nuclide field vector N0. The index I accounts for the time steps. So at every time step, at first the Monte Carlo solver is called, and we obtain the initial neutron flux at the beginning of the time step. After that the burnup solver is called, and it's using the flux which we obtained, and it returns the predictor nuclide field vector for the end of the time step. This vector is then used to obtain the predictor flux. After that, the beginning of step flux and the predictor flux are combined together. We calculate the average value and we call it the corrector flux. The corrector flux is then used to redeplete the system over the whole time step again. So finally we obtain our nuclide field vector at the end of the time step, and this cycle will repeat until we cover the required time period. So let's have a look at the results of a test simulation in which I use the predictor-corrector based coupling scheme between the Monte Carlo and the burnup solver. So this is based on a very simplified numerical model. Actually, the flux solver is not Monte Carlo, it's a deterministic solver, because in order to analyze the stability we don't need necessarily to use the Monte Carlo solver. In this case the system is a slab. It should have cosine like flux distribution if there was no feedback. Nevertheless, we have xenon feedback here, so the flux distribution should be flattened. However, it should be symmetrical. the system is symmetrical with respect to its center, so the solution must be symmetrical. Nevertheless, as you can see, the flux obtained in time step number 100 and 101 is not symmetrical at all. As you can see, it is severely asymmetrical. In fact, the neutron flux at step number 101 does look symmetrical, however it is incorrect. The correct neutron flux should look like this, something like this. So this doesn't look like numerically stable simulation. Interestingly, when you compare the step 100 and 101, you can see that the neutron flux did move, but not considerably. If you remember the simulation I showed in the case of the explicit Euler coupling scheme, the oscillation of the neutron flux was very severe. So the flux was moving over the whole system from one side to the other. So they denoted a very strong spatial oscillation of the neutron flux, as well as the oscillation of the xenon distribution in the system. In the case of the Monte Carlo burnup simulations, which are based on the predictor-corrector coupling scheme, the neutron flux very often does not oscillate that severely. So in our case, when you compare these two time steps, you can see that it did move a little, but not that much. And if you go through all the time steps, you will see that there may be a long series of steps in which the neutron flux actually is pretty much fixed to a distribution which is incorrect. So that is a problem, because if you keep the neutron flux, for instance, in this shape over many time steps, and you use this flux to deplete the system, then you will over deplete the parts in the system in which the neutron flux has its maximum, right? And you will under deplete the other parts in the system. While in case of the explicit Euler-based coupling schemes, we have these severe oscillations which are jumping all over the system, over all the time steps. So even though we very much dislike these kind of oscillations, it will never happen that a certain part of the system will be severely over depleted, because the maximum of the neutron flux will be jumping everywhere. So as you can see, the predictor-corrector based coupling schemes may be very dangerous, because you may receive totally wrong results due to the numerical instability, and yet when you monitor the neutron flux distribution over the time steps, you may not observe large oscillations. So when you use the predictor-corrector based coupling schemes, it's extremely difficult to figure out the error in the final results of your Monte Carlo burnup simulations. And I would rather like to discourage you from using these schemes. So here I have results from yet another test calculation, which is done with the real Monte Carlo burnup code, Serpent. In this case, the system represents a slab. However, it has reflective boundary conditions on both sides, so there is no leakage, and therefore the neutron flux in the system should be flat. I have the time steps set to 30 days, so that's a very large time step, and I have the second and third time step results here. Here you can see the initial flux at the second time step and the predictor flux, and here this is the corrector flux, so that is the combination of these two fluxes together. So we use this corrector flux for the final redepletion of the fuel in the system. So as you can see, the corrector flux is actually a better representation of the neutron flux than the flux from the beginning of the time step, and it's also a better representation than the end of the step flux. However, it is not flat. And if you look at the next time step, you can see that the corrector flux is also not flat, and moreover it has about the same shape as the corrector flux from the second time step. So the middle part of the system is going to be under depleted, while the parts of the system which are close to the boundaries are going to be over depleted. If such a corrector flux remains with this shape over a series of time steps. So that confirms the previous test simulation with that simplified numerical model. You can see the same problem. The neutron flux basically does not oscillate very much. However, it is not correct, and it remains at its shape over a number of time steps. So eventually the errors in the fuel depletion grow over the time steps. So in case of the explicit Euler coupling scheme, since the neutron flux was jumping all over the system, the errors in the fuel depletion were kind of cancelled out over a number of time steps. But in this case they combine. So again, I want to discourage you from using all the coupling schemes which are based on the predictor-corrector method. So finally, let me summarize the lesson. I want to stress that the Monte Carlo burnup coupling schemes which are based on the predictor-corrector method are only conditionally stable, so they are stable with a sufficiently short time step. Now we have seen that the corrector neutron flux, which is used for the final fuel depletion over each time step, may not necessarily oscillate over the time steps. However, it is usually not correct neutron flux, and because of this, the errors in the fuel depletion combine over the time steps. They are not being neglected by each other as in the case of the explicit Euler coupling scheme. So the Monte Carlo burnup simulations which are based on the predictor-corrector method are very often much worse than the Monte Carlo burnup simulations which are based on the explicit Euler coupling scheme. Nevertheless, this conclusion may not be correct for systems in which the xenon oscillations cannot develop. So those are fast systems, or systems in which only one burnup material is introduced, or systems which represent a very small reactor with a small dominance ratio. So in these cases, the predictor-corrector coupling scheme may give better results than the burnup simulations which are based on the explicit Euler. And that's simply because the corrector neutron flux is a better representation than the initial neutron flux over each time step. So that is all for now. Bye!